Welcome. In this lecture, we continue our discussion on the modeling of embedded systems. In the last lecture, we discussed two principal strategies for modeling embedded systems, namely the sequential program model and the finite state machine based model. We also discussed three extensions to the finite state machine model, namely the extended finite state machine or the finite state machine with data path, and then we discussed hierarchical or concurrent finite state machines HCFSMs, in which a state of the FSM could also incorporate another finite state machine, and we discussed mechanisms for expressing concurrent processes and also hierarchical structure in an embedded systems, how to model such concurrent processes and hierarchical processes we understood and saw in the last lecture. We saw two types of decomposition, the OR decomposition for hierarchical OR type decomposition, and the AND decomposition where we could describe or specify concurrent processes. Then we also discussed the program state machine, in which each state of a hierarchical, it was an extension of the hierarchical and concurrent finite state machine, and this allowed each state of the hierarchical and concurrent finite state machine to possibly include sequential programs. So, the description of a state could now include sequential programs. In today's lecture, we discuss a slight deviation of another slight deviation of the finite state machine modeling strategy called discrete event systems. In fact, discrete event systems is not only a modeling strategy, but also allows automatic and correct by construction synthesis of the controller, of the embedded control task or the embedded controller that we want to design. So, this is a strategy which not only allows modeling, but also automatic synthesis of the embedded controller that we intend to design. However, in order to do such synthesis, we need to be able to accurately and formally model each component of the embedded system using the discrete event systems or DES. And if we can model all components of the system, the different processes or functionalities, the different resources, all these, the behavior of all these components, if they can be accurately and completely and formally modeled, then we have a methodology for automatic and correct by construction synthesis of the embedded controller. So, let us discuss this extension of finite state machine called discrete event systems. A discrete event system DES is a discrete state space similar to FSMs, because it has a finite set of states, is a discrete state space event driven system that evolves with the occurrence of events. So, there is a change in state when events occur. Individual, and in this system the supervisory control. So, a discrete event system is a discrete state space similar to FSMs, as FSMs have finite states, this also has a finite set of states. So, it is a discrete state space event driven system that evolves with the occurrence of events. So, there is a change in state when events occur. All components of the system has to be first modeled using such a discrete event system which changes states with the occurrence of events. So, individual components such as functionalities or tasks, resources or processors, other shared resources etc. of the system are modeled by an automata. Now, before going into this automata, so we first discussed, the title of this lecture was supervisory control of discrete event systems. So, what is supervisory control of discrete event systems? The intention of this process of this modeling methodology, modeling in this way, as I told you, is ultimate synthesis of the controller. This controller is called the supervisor, because it controls the behavior of the embedded system, in a way we want it to behave, so that it does not behave in a way that we do not want. So, the behavior is restricted, the unrestricted behavior is controlled by the supervisor. And how does it do? The supervisor enables or disables certain events at each state. Okay. So, it will disable or enforce certain events, or it will not allow certain events, and by that way it will control what the embedded system can do and what it cannot do. Okay. With this introduction, we go into the formal definition of a discrete event system. So, a discrete event system is a six tuple, has 6 tuples q, sigma, q0, qm, del and sigma, where q is a finite set of states like in an FSM. Sigma is a finite set of events. This finite set of events includes both controllable and uncontrollable events. So, if you see this sigma consists of sigma c union sigma uc. Here sigma c denotes the set of controllable events. That means, the supervisor can control or prevent the occurrence of these events. These are controllable by the supervisor. So, the occurrence of these events can be prevented by the supervisor if it so wants. And it also includes union sigma uc. The system will also include uncontrollable events, and these uncontrollable events cannot be controlled by the supervisor. The occurrence of these cannot be controlled by the supervisor. Okay. There are certain events. So, sigma another class. So, we can classify the events in terms of sigma c union sigma uc. Similarly, we can also classify the events as sigma o sigma union sigma uo. So, here sigma o is the set of observable events, those events that can be observed externally. The occurrence of these events can be observed externally, and there can be certain events that cannot be observed from the outside world. So, the set of events will include sigma o union sigma uo. Q0, small q0 belongs to capital Q, is a special event called the initial state. The entire embedded system, this in whatever we are modeling a particular component, if it is, the component will start from this initial state. For example, in our earlier lift controller, the idle state was the initial state of our system for the elevator. Capital Qm belongs to Q, it's a subset of Q, sorry, capital Qm is a subset of Q, is the set of marked states, and it is a subset of states within Q. What do these states specify? These are the states at which the component, the behavior of the component can legally complete. So, these are the completion states, for the legal completion states for the embedded for the system that we are modeling. So, Qm denotes the set of states in which the component can complete its execution. Okay. Del is the transition function. So, del is the transition function from a state within Q, capital Q, and on a particular event from sigma. So, at a given state for a given input, for a given input event. So, I have an event that has occurred at a given state, and on that event I go to the next state, which also is a member of capital Q. So, capital Q cross capital sigma goes to Q is the partial state transition function. So, here is the difference from finite state machine. It is not a total transition function. That means that we do not need to have definition for the transition on all events in sigma. So, on which events in sigma do we need to have this definition of the transition at a given state? It is all those it is for all those events that are defined in gamma, which is next. So, gamma is a part of Q, and is called the active event function. So, there are a set of states called the active event set, meaning that within any given particular state of capital Q, within capital Q I take a state and there I will have an active event set. That means, those events from capital sigma which are legally possible at that particular state. Not all events in sigma will be legally possible at that particular state within the system that we are describing. We will take an example, but this is what it is. So, therefore, del will be defined for only the active event set at a given state. So, a given state has an active event set which is a subset of the it has an active event set which is a subset of the events in sigma, and on those events the del function or the transition function will be defined. Now, we will take first an example of an embedded system, and we will also understand what we want to design. Okay. I will take the example of the very popular dining philosophers problem, okay. And then we will show how automated synthesis from the how individual models can be developed for this embedded system, and then how automated synthesis of the embedded controller can be designed for it. So, now let us first describe the system. The embedded system that we that we intend has two processes, and these two processes or functions we name philosopher 1 and philosopher 2, and there are therefore, these two philosophers are two processes in the embedded system that we two processes or functionalities in the embedded system that we want to design. Two philosophers are seated on either side of a table. So, this is how it is defined. Two philosophers are seated on either side of a table with a plate of food in front of them. So, these two philosophers are two processes, and the two plates of food are the input data that these processes will consume. So, two philosophers are seated on either side of a table, these are two programs or processes, and there is a plate of food that this program will execute with, okay, in the front of each of them. These are the data, the plates of food are data. Only two available forks. So, these forks are resources, but we will talk about the resources a bit later. So, what are these forks? We can but we can understand what these forks are. These forks are the processing resources based on which the philosopher will execute its function. So, the process philosopher will execute using the forks. So, it will execute using the processing resources, and what will it do? The process is of eating. So, the processing that it will do using the resource fork is eating of what? The data, which is the food. So, we have only two available forks. A philosopher can only be in either two states. It is the philosopher is either thinking or it is eating, okay. And to transit to the eating state from the thinking state, the philosopher must pick both forks one at a time from the table in any order. Now, how can the philosopher transit from thinking to eating? What will be the events? So, initially it will be in the thinking state, and then it will pick one fork. So, the event will be the picking of the fork. So, taking a resource, and it will have to take both resources, both the forks, in order to be able to eat. And this consumption of the resource, this taking of the resource, that will happen one after another, not together. So, to transit to the eating state from the thinking state, the philosopher must pick both forks. It requires both the resources one at a time from the table in any order. After eating, a philosopher puts back both forks and starts thinking. So, after eating is complete, after the processing is done, it will relinquish the resources. Firstly, it captures the resources and eats, and then after eating is done, it relinquish the computing resources together, okay, both forks, and then it starts thinking and goes back to its initial thinking state. Now, what given this, so I in this embedded system I have two concurrent processes, two processes that will run, and these are two philosophers which wants to eat food placed in terms placed in front of them. Each of these philosophers can be in two states, either thinking or eating. In order to eat, they will have to pick both forks, eat. So, both the philosophers cannot eat simultaneously, right. So, the objective of the embedded controller is exactly to enforce this. Design a controller that enforces mutual exclusion by disallowing a situation in which each philosopher holds one fork and waits for the other fork indefinitely. Now, we said that a philosopher will pick the forks one at a time. So, a situation can therefore happen that, let us say, philosopher 1 has picked one fork for eating, and at the same time philosopher 2 also wanted to eat, and therefore, it picked the other fork. And then what happens is that both the processes, both the philosophers are waiting for the other fork, and nobody can start eating because the other fork or the other resource is taken by the other philosopher. So, the objective of the embedded controller is to enforce mutual exclusion by disallowing a situation in which each philosopher or each process holds one fork or takes one resource and waits for the other resource indefinitely, leading to a deadlock. With this definition, let us go about the modeling. Firstly, we define the events. The event of picking a fork by a philosopher is controllable. Okay. So, the supervisor can control whether a philosopher can pick a fork, can take a resource at a given time or not. So, it will allow or disallow a philosopher or a process to be so that it will be able to pick a resource or not, while the event of returning forks is uncontrollable. So, after eating the supervisor cannot control it from relinquishing the resource, from leaving the resource, right. Okay. So, what are the description of events? So, we now symbolically describe the different events and name the different events symbolically. So, the first event is F11. So, F11 means philosopher 1 picks up fork 1. F12 means philosopher 1 picks up fork 2. F21 means philosopher 2 picks up fork 1. F22 means philosopher 2 picks up fork 2. RF1 means philosopher 1 puts both forks down, RF1, relinquishing fork 1. So, relinquishing forks by philosopher 1. So, RF1 means philosopher 1 puts both forks down, and RF2 means philosopher 2 puts both forks down. Now, what are the set of controllable events in this? Sigma C. Sigma C are F11, F12, F21, F22. So, the picking of the forks either by philosopher 1 or philosopher 2 is controllable by the controller, controllable externally, controllable by external entities which can control the embedded system. And the occurrence, while the occurrence of the relinquishing of the resources fork 1 and fork 2 is uncontrollable. So, sigma UC is RF1 and RF2. Now, before the design begins, we first model each of the components in the embedded system using the discrete event system model. So, first philosopher 1. So, what does it say? Firstly, the initial state is T1, that is philosopher 1 is in the thinking state. When after some time, let us say philosopher 1 wants to eat, and therefore, let us say he picks fork 1. So, therefore, the event is F11, philosopher 1 picks fork 1. When he does this, it goes to the intermediate state I11. In this state, philosopher 1 has picked up fork 1. and then after this intermediate state, philosopher 1 will then pick the other fork. So, at I 1 1 he can pick fork 2, which is F 1 2. So, philosopher 1 picks fork 2, and after this he has picked both forks and he goes to the eating state E 1. After eating, he reads both forks using R F 1 and goes back to thinking state T 1. Similarly, if he picks fork 2, so F 1 2. So, at the thinking state he could have first picked fork 2. So, from T 1 on event F 1 2 it would go to state I 1 2, which is another intermediate state in which so what is this intermediate state I 1 2? Philosopher 1 has picked fork 2 and has not picked fork 1, that is I 1 2. After he picks up fork 1 at I 1 2, he goes again to the eating state E 1. So, philosopher 1 now again has both forks and he is eating. After eating is complete, he relinquishes both the forks and goes back to the thinking state. This is the behavior of philosopher 1. A similar behavior also goes for philosopher 2. So, either he is initially in the thinking state T 2 and then he can pick, let us say, fork 1, which is F 2 1. So, philosopher 2 picks fork 1 F 2 1 and goes to the intermediate state I 2 1. So, this is the intermediate state in which philosopher 2 has picked up fork 1 and has not picked up fork 2, and then he picks up the other fork and goes to eating in a very similar way as that for philosopher 1. Now, how does the resources behave? So, this is how the two processes in our embedded system behaves. How does the resource, how do we model the behavior of the resources? The resources can either be in available state or in the used state. So, fork 1, that is the resource 1, is first initially in the available state A 1, and how can it go to the used state U 1? Either through the event F 1 1, meaning that philosopher 1 picks up fork 1, or through the event F 2 1 in which philosopher 2 picks up fork 1. So, in either of these two ways it goes from the available state to the used state. Now, after U 1 it goes back to the available state either on event R 1, R F 1 or R F 2. So, either philosopher 1 relinquishes the resource fork 1 or philosopher 2 relinquishes the resource fork 1. In either way it goes from the used state back to the available state. And this is the same, similar behavior also holds for fork 2. So, it is in the initial state A 2. Now, what are the events that that can take it to the used state? Either philosopher 1 or philosopher 2 picks up fork 2. So, F 1 2 philosopher 1 picks up fork 2 or F 2 2 philosopher 2 picks up fork 2. In either way it goes from available state to the used state. At the used state after eating, it goes back to the available state through the events R F 1 or R F 2. So, fork 2 is relinquished by either philosopher 1 or philosopher 2. In either case it goes from used state back to available state. Now, how do we model the concurrent behavior of different components in the embedded system? So, before we go about the design of the controller, we have to define the concurrent co-execution behavior of the different components of the embedded system in order to obtain the overall behavior of the embedded system. First, we are modeling. So, what are we modeling? The behavior of the embedded system. First, we are going bottom up. First, we have modeled the individual components, philosopher 1, philosopher 2, resource 1, resource 2. Now, slowly we have to obtain the concurrent co-execution, uncontrolled concurrent co-execution behavior of the entire embedded system, on which control needs to be imposed. So, how do we get the concurrent behavior of such an embedded system modeled component wise using DES? Through the composition of the DES, through parallel composition. So, concurrent behavior is modeled through the parallel composition of DES. So, let us consider two DESs G1, that is Gi. So, the first DES G1 is Q1 sigma 1 del 1 gamma 1 Q01 and Qm1, and similarly I have G2 which is Q2 gamma sigma 2 del 2 gamma 2 and then Q02 and Qm2. The parallel composition of these two is defined as G1 parallel G2 equals to accessible part, that AC you see is the accessible part of Q1 cross Q2. That means you have a composition of G1 and G2. What will be the possible number of states in the composite automata combining the behavior of G1 and G2? It will be the number of states in G1 product the number of states in G2. So, Q1 Q1, Q1 Q2, Q2 Q2, Q1 Q3. So, these will be the states in the so Q1 of G1 and let us say Q1 of G2, this can be one state of the composed embedded system. So, the product, so the number of states will be the product of the number of states in Q1 with the number of states in. So, these are pairs of states of individual automata. So, this will be the number of states in the composed automata. So, what will be the number of events? Sigma 1 union sigma 2. So, there could be some events that are not there in say G2, those events will be there in the composed automata. There can be some events which are there in G2, but not which are there in G1, but not in G2, that those will also be there in the composite automata, and the common events of G1 and G2 will also be there in the composed automata. So, therefore, the events in the composed or composite automata are sigma 1 union sigma 2. Del is the transition function which we describe next. Sigma 1 parallel 2. So, this is the active event set. We will just see that we will also describe this next. The initial states are the individual initial states. So, Q01 comma Q02. So, we say that the states are states of the composite automata are pairs of states of the individual automatas, right. So, what do we mean by this? What do we mean by the composite automata? We are saying that the composite automata is composed of individual automatas running concurrently. So, during the concurrent execution of the individual automatas or processes, at any given time, let us say you have two automatas G1 and G2, G1 will be at a certain state and G2 will be in another certain state. So, if we consider what will be the composite state, it will be composed of that state where it is currently in G1 and that state where it is currently in G2. So, let us say it is in Q1 of G1 and Q2 in G2. So, Q1 Q2, Q1 comma Q2 is the composite state in which the overall embedded system is in at a given time, at that given time. So, what is the initial state? It is that pair state Q01 Q02 which consists of the initial state of both the automatas. And the marked states again are the product of the marked states in both the automatas Qm1 cross Qm2. Now, we go into the transition function the transition function del. Now, we will consider an example in which let us say I have an event small sigma and the composite state in which currently the composite automata is q1 of g1 and q2 of g2. So, the state of the composite automata is q1 comma q2, and we want to know what happens when this event small sigma occurs at the composite state q1 comma q2. Now, there are three separate cases. That first, the first case is that this small sigma is in the active event set of both q1 in g1 and q2 in g2. So, if sigma is defined or sigma is part of the active event set of q1 of g1 and q2 of g2, then the first line of the RHS of this equation comes in. So, the next state is going to become del 1 q1 sigma comma del 2 q2 sigma. So, the composite state in which the automata will go from q1 q2 is that pair state which is defined by where q1 would go on sigma and where g1 would go on this small sigma from q1 and where g2 would go on small sigma from q2. That pair state which is defined by what? Del 1 q1 sigma comma del 2 q2 sigma. So, it would go to that state. Why? Because this small sigma is defined on both q1 and q2. Now, let us say sigma is not defined in the entire behavior of G2. So, the second line comes in the second line in the RHS says that when sigma belongs to, so if you see in the RHS, when this happens, when if sigma small sigma belongs to gamma 1 q1, that is it is in the active event set of G1 at q1, but it is not defined in G2. So, it is not part of capital sigma 2. Okay. So, if that happens, then the next state. So, if that happens, so it is not defined in q2 of G2, because sigma small sigma is not defined in q2 of G2. It cannot go anywhere from q2 at G2. So, therefore, the next state will be del 1 q1 sigma, because small sigma is defined in q1 of G1. So, it can move from q1 to somewhere to the next state from q1 on small sigma. So, therefore, del 1 q1 sigma is defined and it will remain in q2 for G2. So, the next state will become del 1 q1 sigma comma q2. The third line of the RHS happens for the opposite case. So, let us say small sigma is not defined as part of the active event set of q1 in G1, but small sigma is defined as part of the active event set of q2 in G2. Therefore, in that case the next state would be q2 comma del 2 q2 comma sigma. So, it will remain in q1, the automata, the composite automata is going to remain in q1 state of G1 and it is going to move to the next state in G2 from q2 on the event small sigma. So, therefore, the next state becomes q1 comma del 2 q2 comma small sigma. It is undefined otherwise. For example, let us see what can be an undefined case. Let us say that small sigma is defined as part of, let us say small sigma is defined as part of capital sigma 2, meaning that small sigma is a valid event in G2. However, it is not defined at state q2 of G2. Small sigma is not defined at the state q2 of G2. However, small sigma is a valid event in sigma 2. So, it is part of the active event set of some other state in G2. It is not defined in Q2, but it is part of the active event set of some other state in G2. It is not completely undefined. So, therefore, it is a part of capital sigma 2. If that happens, then the second line cannot take place. The second line of the RHS, the second line of the RHS in the equation cannot take place. So, so del 1 Q1 comma sigma comma Q2 cannot happen if small sigma is part of capital sigma 2, although it is not defined in Q2. Okay. So, it is not defined in Q2, but it is part of the active event set of capital sigma 2, then the second line of the RHS cannot happen and it will become undefined. Okay. So, then comes what is capital gamma 1. So, what do we mean by the active event set at Q1 Q2 of the composite automata? So, the active event set of Q1 at the state Q1 Q2 of the composite automata is defined as follows. It is sigma 1 Q1 intersection sigma 2 Q2. So, whatever is the common active events at Q1 and Q2, those events are part of the active event set of Q1 Q2 first. So, it is composed of 3 components, right. So, union it has 2 union operators in operations in between. So, I am talking of the first part. The first part sigma 1 Q of the RHS, the first part of the RHS, what does it say? Sigma 1 Q1 intersection sigma 2 Q2. What does it mean? So, all the common active events at Q1 and Q2. So, those are part of the composite active event set of the composite state. What else is part of the active event set of Q1 Q2? Those events that are defined as part of Q1. So, it is part of the active event set at state Q1 of G1, but those events are not defined in the entirety of G2. Those events will also be included as part of the active event set of Q1 Q2, and then the opposite as well. Those events that are part of Q2 of G2, but are not defined in the entirety of G1. So, it is not part of capital sigma 1. Those events will also be included in the active event set of Q1 Q2. Now, as I told, accessible part, what does this accessible part of tell me? The accessible part of the composite automata. So, we say that G1 parallel G2 is the accessible part of the composition that we have obtained through this. So, what is the accessible part? Denotes the operation of deleting all the states of G. So, after all this operation that we have got, this composition operation, we can get some states which are not reachable from the initial state of the composite automata. So, those states which are not reachable from the initial state of the composite automata will be deleted. So, ACG denotes the operation of deleting all the states of G that are not reachable from the initial state of the composite automata. So, this is the definition of synchronous parallel composition, and with this definition we will see how we slowly built the behavior, the composite co-execution behavior of the embedded system that we are given. The embedded system consisting of 2 parallel processes, P1 and P2, the 2 philosophers, and the 2 resources F1 and F2. So, first we will see for the resources, because first we will try to compose the 2 resource models. So, we will try to find out what happens, what is the possible concurrent behavior and the states that are there, that will be there in the concurrent behavior of the 2 resources. What are the possible states that can happen when these 2 resources are being used concurrently? What are the possible states that can happen when these 2 resources are being used concurrently? This is what we will see. So, the left one is fork 1 or resource 1, the right one is fork 2 or resource 2, we have seen. So, what are the events, what are the possible events for resource 1 or fork 1? F11, F21, RF1 and RF2. Either philosopher 1 picks up fork 1 or philosopher 2 picks up fork 1, and then both either philosopher 1 or philosopher 2 relinquishes fork 1. Similarly, for fork 2 or resource 2, the events are F12, F22, RF1 and RF2. Now, what are the common events? What are the common events in F1 of the two resources? So, sigma F1 intersection sigma F2 is RF1 comma RF2. Hence, in the during the transition, when defining the transition, F1 and F2 must synchronize on RF1 and RF2. Because RF1 and RF2 are defined as part of both automata, then they must synchronize. I cannot take the second line and third line of the RHS of the transition function defined in the earlier in the earlier slide. For the transition function, only the top line will be applicable, the top line where I go del 1 and del 2 both are applied. So, if sigma belongs to gamma 1 cross 2 q 1 comma q 2. Okay. So, F1 and F2 must synchronize on RF1 and RF2. And what are the events that are defined in F1 but not in F2? F11 and F21 are defined in F1 and not in F2. And what are the events that are defined in F2 and not in F1? F12 and F22. So, the event of picking up the forks by picking up fork 1 by philosopher 1 or philosopher 2 is defined in the resource model of fork 1, but not there in fork 2. Similarly, the events of picking up fork 2 by philosopher 1 or philosopher 2 is defined in the resource model of F2 and is not part of F1. Now, the number of states in the composite model will be given by QF1 cross QF2 and is equal to 4, because fork 1 has 2 states and fork 2 has 2 states. So, the total number of states in the composite model will be QF1 cross QF2 equals to 4. And what are the states? The initial state will be Q01 comma Q02, which is A1 comma A2. A1 is the initial state in F1 and A2 is the initial state in F2. So, initially the composite automata is in state A1 A2, and because it is also the marked state, it has 2 circles. So, marked states I forgot to tell previously, marked states in the automata are represented by these double rounded circles. Okay. So, the automata finally, why are these double rounded circles there? It says that it is initially in available state, then it is in use state, and then finally it will go back to the available state when process 1 will relinquish, let us say any process will relinquish fork 1. In F1, say in F1 it goes from A1 to use state and then goes back after it is relinquished, it goes back to A1, and that is its idle or initial state, and also that its final or marked state. So, therefore, in the composite automata A1 A2 is the initial state and also the marked state. At A1 A2, either philosopher 1 or philosopher 2 will first pick up, let us say, fork 1. So, if it can take an event for the let us say the event that fork 1 is picked up. The event fork 1 is picked up is represented by the arrow going from A11 to U1 comma A2. Okay. So, when fork 1 is picked up either by philosopher 1 or philosopher 2, that can happen through the events either F11 or F21. If either of these two events occur, fork 1 goes to the used state and fork 2 remains in available state. So, the state that it goes to is U1 comma A2. How does this happen? Because this let us say F11 has occurred at A1 A2. So, A1 A2 is the state and F1 has occurred. So, del A1 A2 comma F11 will be what? Will be del 1 A1 comma F11 comma A2. Why? Because this event F11 is defined as part of F1, but it is not defined as part of F2. So, capital sigma 1 contains F11. So, capital sigma F1 contains F11, but capital sigma F2 does not contain F11. So, line 2 of the transition function will be applicable. So, therefore, from A11 in the composite automata, from A1 A2 in the composite automata, the next state that will be the transition will happen on F11 will be to U1 A2. Similarly, the transition can happen on F21. At U1 A2, what has happened? Fork 1 has been used, but fork 2 is available. Now, the next fork can be picked up. The next fork will be picked up. When the next fork is picked up, both the forks go to U state. So, at U1 A2 on event either F1 2 or F2 2. So, fork 2 is picked up either by philosopher 1 or philosopher 2. This happens and it goes to the composite automata goes to the state U1 comma U2. Similarly, at A1 comma A2, I can reach the fork 2 can be picked first at A1 comma A2, fork 2 can be picked first by either philosopher 1 or philosopher 2. If this happens, the lower edge will be taken from A1 A2, the lower edge will be taken and the automata moves to A1 comma U2. So, from A1 comma A2, F1 on the transition on the event F12 or F22, you move to the composite automata moves to A1 comma U2, in which fork 1 is in available state because it is not picked, but fork 2 is in used state. And then from A1 comma U2, the other fork, which is fork 1, will be picked either by philosopher 1 or philosopher 2. So, from A1 comma U2 on the event F11 or F21, I will again go to U1 comma U2. Now, once I am in U1 comma U2, that is both my forks are in U state, I will go back to A1 comma A2 either on RF1 or RF2. So, my composite automata will go back to the available state on the event RF1 or RF2. So, either philosopher 1 relinquishes fork 1 or philosopher 2 relinquishes both the forks, or either philosopher 1 relinquishes both the forks or philosopher 2 relinquishes both the forks, and then both the forks go from U state back to A1 A2, which is the initial and marked state. So, this represents the concurrent behavior of the resources. Similarly, I can obtain the concurrent behavior of the philosophers, of the two concurrent philosopher functions in my embedded system. Now, what do I want to obtain? The concurrent behavior of the two processes of the two individual functions in the embedded system. This is what I want to obtain. So, these two philosophers we have already modeled and seen how they are modeled. And in this one, the point to note is that sigma P1, that means the event set, the total set of events that are possible in P1 are F11, F12 and RF1. So, F11, that is philosopher 1 picks up fork 1, F12, that is philosopher 1 picks up fork 2, and RF1, that is philosopher 1 relinquishes both the forks. These events are defined in P1. What are the events that are defined in P2. What are the events? F21, F22 and RF2, that is philosopher 2 picks up fork 1 or philosopher 2 picks up fork 2 or philosopher 2 relinquishes both the forks. So, and there are no common events. So, they do not need to synchronize on any events. Why? Because sigma P2 intersection sigma P1 is phi. So, there are no common events as part of this one, sigma P1 intersection sigma P2. What will be the number of states in the composite automata? 16, because there are 4 states in P1 and 4 states in P2. So, 4 cross 4 is 16. And this is a partial concurrent execution model for P1 and P2 together, because the number of states are large, 16. So, we have shown this concurrent behavior here. So, let us take 1 or 2 states and how this happens here. So, initially the concurrent automata will be in T1 comma T2. So, both philosophers are in thinking state. Now, from this thinking state, so the program for T1, let us say the program for philosopher 1 that picks up or asks for the resource or takes up the resource fork 1. So, philosopher 1 picks up fork 1. Then what happens? When philosopher 1 picks up fork 1, we go to the state I11 comma T2. So, for the first automata, philosopher 1 goes to the intermediate state at which it has picked up fork 1 and has not picked up fork 2, and philosopher 2 is still in the thinking state. Why this is feasible? Because F11 is not defined as part of the behavior of philosopher 2, because F11 is not defined. So, line 2 of this definition of the transition function, line 2 of the RHS of the definition of the transition function can be applied, and by that we move from T1 to T1 comma T2 to I11 comma T2. And then if philosopher 1 let us say happens to pick both the other fork as well, that is on event F1 comma 2, then I move from E1 comma T2, that is philosopher 1 moves to eating state and philosopher 2 remains in thinking state. Okay. So, likewise we get the composite model for the philosophers for the concurrent behavior, concurrent co-execution behavior of P1 and P2 by the composite automata P1 parallel P2, whose partial diagram is shown here. Now, given the composite model for both the processes and both the resources, so I have P1 comma P2 partial diagram shown in the previous slide, which is on the left, and on the right I have F1 parallel F2. So, P1 parallel P2 and F1 parallel F2 is on the right side, and these two are the individual composite models for the function, that is the functions and the resources. Now, when the resources and the function work together, the composition of F1 and F2 gives the composite system model. The system model consists of the processes that will be executing and also the resources which will be consumed by the processes. Now, the behavior of the resources when composed with the behavior of the processes gives the composite system model PF, and that is given by P1 parallel P2 parallel F1 parallel F2. And here we see that sigma of P1 parallel P2 has all the states, has all the 6 states that we have defined, and F1 parallel F2 has all the 6 states that we have defined. Therefore, the composite automata must synchronize on all events. So, only the first line of the transition function. So, again the transition function del q1 q2 comma sigma goes to del 1 q1 comma sigma comma del 2 q2 comma sigma. This is the only applicable one, because all events are common. All events are common in both the automata, and hence they must synchronize on all events. And because this is going to be a big automata, we again show a partial diagram. So, let us take the initial state of the composite behavior. So, what is the composite behavior? The philosophers are in state are in thinking state and the resources are available. So, T1 comma T2 the philosophers are thinking and A1 comma A2 the resources are available. Let us say in this state you take the event the event F11 occurs. So, if F11 occurs, then in P1 parallel P2 I must go to I1 comma T2. Okay. So, I will go to I1 comma T2 and it is F11 is also defined F11 is also defined in F1 parallel F2 at A1 comma A2 at the available state, and so F1 parallel F2 moves to U1 comma A2. Okay. And by using the transition function we move to the state I11 T2 U1 A2. So, I move to I11 comma T2 of P1 parallel P2 and U1 comma A2 of F1 parallel F2. So, in the composite automata I move to I11 comma T2 comma U1 comma A2. And then let us say at the state I11 comma T2 U1 comma A2 the event F22 occurs. What is event F22? Philosopher 2 picks up fork 2. So, remember F11 occurred previously, meaning that philosopher 1 had picked up fork 1 and then we move to I11 T2 U1 A2 and now philosopher 2 has picked up fork 2. So, I move to I11 comma I22 and U1 comma U2. So, what is the event? Let us say if you look at P1 parallel P2 and I am at state I11 comma T2 and the event F22 occurs, we see that we move to the state I11 comma I22 and let us say we are at U1 comma A2 and the event F22 occurs. Where do I and the state F22 occurs and I go to the state U1 comma U2, that is both the forks are used. So, now I have reached a state where both the philosophers are in their intermediate states, none of them has reached the eating state and both the forks are in their use state. Why? Because philosopher 1 has picked up fork 1 and philosopher 2 has picked up fork 2, none of the philosophers have been able to pick both the forks. Now, at this state we see that there are no common events, meaning that at I11 comma I22 none of the events that are active at U1 comma U2 are defined. So, what are the events that are active at U1 comma U2 of F11 parallel F22? Only RF1 comma RF2. So, RF1 and RF2 are defined as active events at U1 comma U2 of F1 parallel F2 and these two events are not defined on I11 comma I22. Similarly, so the automata cannot move from the composite automata cannot move from the state I11 comma I22 comma U1 comma U2 because RF1 comma RF2 is not defined at this composite state. Similarly, F1, F2 or F11, F12, F21, F22 all these the picking up of forks, these are not defined in U1 comma U2, okay, but is defined in I11 comma I22. So, on these events you cannot move. So, there is no way on which you can move in the composite automata from the state I11 comma I22 comma U1 comma U2. There are no defined active events on which you can move, and therefore, the final marked state of this automata has still not been reached, because the marked state is what? T1, T2, A1, A2, T1, T2, A1, A2, and that state has not been reached. Hence, we have reached a deadlock in which there is no way in which I can move to the marked state. So, therefore, this concurrent uncontrolled behavior of the system contains deadlock states which must be avoided by the controller. And it is absolutely possible that you can reach these deadlock states if not controlled appropriately, and you will never be able to reach the marked state, and you will remain deadlocked with none of the processes being able to move in the embedded system. So, if we draw this if we do this composition completely, we get this composite automata on the right. The very partial automata that we showed in the previous slide, here on the right side, C part on the right side, this path or this two transitions can be seen how here. So, from T11 in the, if you see the right automata, if you see the right composite automata, from T1, T2, A1, A2 on F1 I go to I11, T2, U1, A2, and then I take F22 to come to the deadlock state. So, this path is present in here. So, this represents this figure, this model on the right that you have represents the composite behavior over using all the resources and processes that I have in the embedded system. Now, given this, I have to be able to control this automata. I have to control this concurrent unrestricted behavior. So, how do I control this concurrent unrestricted behavior? By designing a specification that we want. So, what do we want? We want that if fork 1 is picked up by philosopher 1, only he should be allowed to pick fork 2, or if fork 2 is picked up by philosopher 1, only he should be allowed to pick fork 1. The other way, for philosopher 2, if philosopher 2 picks one of the forks, only he should be allowed to pick the other fork. And this is say enforced by this specification automata here, which we need to define or model. So, in the specification or in the legal specification that we want, in the initially I am in state I 0. At state I 0, either philosopher 1, if I take the top transition, the transition on the top, what happens? Either fork 1 or fork 2 is picked up by philosopher 1, and I go to intermediate state I 1. So, intermediate state I 1 tells me that philosopher 1 has picked up either fork 1 or fork 2. At I 1, therefore, what are the valid events that I should allow? I should allow philosopher 1 only to pick the other fork. So, the valid events at I 1 are F11 or F12. That means, philosopher 1 should be allowed to pick the other fork. So, if I have reached I 1 from I 0 on F11, then I will allow F12 to occur at I 1, so that I can go to I 3. So, if I have used up F11, F11 is no more possible at I 1, because fork 1 has already been picked. So, F11 is not possible. So, what is possible and allowable only is F12. So, I should disallow F22 at I 1. Similarly, if you look at the transition at the bottom, from I 0, philosopher 2 can pick either fork 1 or fork 2 and move to I 2, and the other fork philosopher 2 can only be allowed at I 2, philosopher 2 is only allowed to pick the other fork and move to I 3. At I 3, either philosopher 1 or philosopher 2 relinquishes both the forks and moves back to I 0, which is the marked state as well. So, it is the initial as well as the marked state. Now, given this legal specification, what we do is then compose parallel composition, a similar parallel composition of the system of the specification and the unrestricted behavior. So, we compose the specification, which is what the system should do legally, and the unrestricted behavior. And when we do that, we obtain a supervisor or the controller, which is shown at the bottom at the right of the arrow. So, at the right of the green arrow shows what is the supervisor that we get through the composition. Let us see one or two states how this transition system or the supervisor is obtained. So, initially I will be in T1, T2, A1, A2 of the unrestricted composite behavior, and I will be in state I0 of the specification. At that state, let us say I allow F11, the event F11 occurs. So, where will I go? I will go to state I1 of the specification and to the state I11 T2 U1 A2 of the composite unrestricted system model. So, at this system model we see that if I am in state I11, F22 is not defined. However, F22 is defined in the automata. So, the transition system, because all events, both the events in the specification and the events. So, we have a total of 6 events and all the 6 events are there in the specification, all the 6 events are there in the unrestricted behavior. So, during composition the system must synchronize on all events. Okay? The composite system must synchronize on all events. So, therefore, only the first line again going back of the transition system del is applicable, of the transition function del is applicable. Okay. So, because F22 is not allowed at I1, so in the composite behavior, in the composite controlled behavior, the event F22 will be disallowed. So, there will be no event in the composite behavior. I cannot go from I1 I11 T2 U1 A2, which is the composite state, and go to a state such as I1 I11 I22 U1 U2. Such a transition is not allowed. Now, if we see the composite automata, the supervisor figure here. So, initially I am in state 0, I go to F11 and I move to the state 1. At state 1 of the supervisor or the controller, I see that the event F22, as we discussed, has been disallowed. I have not allowed F22. What have I only allowed? The only possible allowing, if we go back to the specification at I11, the 2 events that are possible are F11 and F12. And because F11 has already been taken, the only event that is possible is F12. So, at 1 I allow F12 to happen and I go to 5. Therefore, the specification when I compose or parallel compose the specification with the uncontrolled behavior, I get the supervisor which disallows transition to the deadlock states of the the composite behavior. Okay. So, the event, the controller will only allow those events which do not lead to deadlock states. The controller or the supervisor is such that it allows only those events which disallows transition to the deadlock states. Now, after this, finally, how does it occur? How does the entire system function? I have the unrestricted system, which is the system behavior, the physical system. Now, let us go back and think of the cyber physical system or the control system that we had defined, the cyber physical system or the control system that we had defined in lecture 1. We had a physical system, which is the system in green shown here. We had a controller which controls the physical system, which is shown in yellow over here, that is the supervisor. I sense what is the current state of the physical system through a sensor, that is fed to the controller, and the controller generates appropriate actuation actions. Now, suppose the initial system, at the initial state of the system, F11 is taken. So, I know that the sensor tells me that I was in the system, I am in state 1 and I have taken the event and the event F11 has occurred. So, the supervisor sends from the sensor the input that I am in state 1 and event F11 has occurred. This goes to the supervisor, and the supervisor then says that what are you allowed to do? You are allowed to take only the supervisor therefore goes similarly supervisor accordingly goes from the initial state on F11 goes to 1, and then the supervisor says that you are only allowed to take F12 and you are not allowed to take F22. So, the actuation it tells the actuator that please tell the physical system to only allow F12 and not allow F22, because F22 will lead to a deadlock state, and thereby we have obtained the controller which controls the physical system. So, in this lecture what we have studied? We have studied how to formally model the behavior of the entire system, and we studied how to obtain a controller. Now, there are tools such as Supremica, TTCT, there are automated tools where you can define these individual models, and there are automated. So, these formal transition methodologies on which these transition functions will be automatically applied, the tools will automatically apply this transition function, compose them, and we will have a correct by construction supervisor or controller depending on the behavior. So, if the behavior of the system has been modeled correctly, if the specification has been modeled correctly, then we have a correct by construction procedure by which we will obtain a supervisor or controller for the system that can be applied on the physical system to control it appropriately. With this, we come to the end of this lecture.